Hi, you're 11. We're looking at Booklet C now, and this is part 1 of Booklet C. We might not take this in order though. I might pick out some random ones here, and this will probably be done in 2 parts this video, but we're definitely going to start off with circle theorems. In this booklet I've kind of given you some revision cards on the front, although they're not that obvious to see what's going on. Let me run you through the circle theorems, okay, before we do the questions. The first one, you're looking for this kind of setup, alright? Obviously they're all in a circle, but the setup you're looking for is that, okay, where that angle there, the angle at the centre, this needs to be the centre of the circle, is double the angle on the circumference. So the rule is the angle at the centre is double the angle on the circumference, or vice versa, the angle on the circumference is half the centre. The next one, which is this one here, okay, the wording is there. Instead of going to the centre, if we did the same thing and went to there, but we went to the circumference somewhere else, so that's the kind of setup you're looking for. Okay, they are equal. So rather than the one at the centre being double, angles at the circumference are equal. The third one, with the third one, you're specifically looking for a diameter. If there's no diameter in the question, this is not one to even concentrate on. But if you can see a diameter, a line through the centre, then from the ends of that diameter you make, pretend this is a diameter over here, if you then touch the circle somewhere else on the circumference, that is a 90-degree angle. The wording you would use is the angle in a semicircle. Obviously when you draw a diameter you split the circle in half, so the angle in a semicircle is 90, and it doesn't matter where it is. Even if I came this way and went across to that diameter, that would be 90 as well. Okay, then you've got this one. I'm jumping here to the cyclic quadrilateral, the 4-sided shape with all the corners touching the circle. That's important. It's got to be inside the circle and all 4 corners touching. In a cyclic quadrilateral, a quadrilateral in a circle, opposite angles, so these two will add up to 180 and these two will also add up to 180. There's your basic 4. Okay, there's your basic 4. Then you've got 2 linked to tangents, right? This line outside the circle. Number 1, if you draw a tangent and join it to the centre, a tangent meets a radius at 90 degrees. That's the first one. And then the slightly tricky one, if you've got a tangent and instead of joining it to the centre, say you come from this direction and from there you go back on yourself and you kind of make an angle there, this red angle here. So a tangent meter, what we would call a chord, but you don't need to know that, okay? From this line, this chord, if you make a triangle, this angle here from this chord will be equal to this one, and this is called the alternate segment theorem. The alternate segment theorem, it's just, you only need to remember those 3 words, okay? But by the same token, if we came in from this direction and went back on ourselves there, and we went from there up to there, then he'd be the same as him. Right, let's get into past paper questions on circle theorems. Starting with question 1. Now, I can straight away see the tangent, okay? So I'm down to kind of 2 circle theorems I can use. Is the tangent connected to the centre of the circle? No, I'm not even sure where the centre is, so I'm not using that one. Tangent to radius is 90. But what about this alternate segment theorem? If I come from this direction, back on myself, they are the same, from there. Or if I come from this direction and back on myself using that line there and going up there, they are the same. So the one they want is m is the same as 60, and the reason I've given is the alternate segment theorem. You might want to do these one ahead of me, you know, and then just kind of catch up, hit pause as you're going along, but I'm going to just keep going. You pause as you need to. This one, no tangents, so forget those, so we're down to 4 already. The one interesting shape that I've picked out here straight away, if you look at my red lines, you've got that kind of arrowhead. So I think with that one I'm probably going to be using that is double that. The angle at the centre is double the angle of the circumference. But ignoring that and looking here at A, D, C, B and back to A, I've got a 4-sided shape inside a circle. I've got a cyclic quadrilateral and the opposite angles add up to 180. So if that's 140, that's 40. Reason, opposite angles in a cyclic quadrilateral add up to 180. Once I know that's 40, that's 80. Reason, angle at the centre is double the angle at the circumference. Moving on. Quite a neat setup on this one, I thought. I haven't actually done this one, so let me fill this in. Now, I thought for a minute I could use this tangent kind of goes to the centre and makes a 90-degree angle. And I probably will use that in a second, but then what I'm actually looking for here is angle OQR, which is this blue one here. Now, this blue is the same as this blue because these are both radiuses of the circle, radii of the circle. This is a little isosceles triangle, and because these tangents come from the same point, this length here is the same as this one here, so this is another isosceles triangle. So I've got two equal angles in this isosceles triangle and two equal angles in this isosceles triangle, the blue one. Now, knowing that that is 30, I could work out this, okay. 180 take away 30 is 150, split it in half, they are 75 each. Alright, I'll write that down here. Angle PQR, this red one here, put a little roof on the Q because that's where I'm at, PQR, this red one is equal to 75 because of two equal angles in isosceles triangle, and I'm going to go overboard here and really describe it, and the triangle I'm talking about being isosceles is QRP. It doesn't matter which way around those letters are, so that's that. The red and the blue, the other rule I'm using here is the tangent meeting the radius. And my rule was if I had a tangent with a radius, it makes 90. Well, if that red bit is 75 of the 90, the blue, so what I'm looking for, which is OQR, must be 15, as a tangent meets a radius at 90 degrees. Okay, that's that one. This one. Quite easy again, okay, this isn't a diameter, I can't see any tangents, no diameters, I can't see that arrowhead sort of shape. The only thing I'm really left with is the cyclic quadrilateral, which I can see being ADCB, ignore this line for a minute. Opposite angles in the cyclic quadrilateral add up to 180. 180 take away 71 means that this is 109, you can see that there. And then I'm just using the basic rule that the three angles in a triangle add up to 180. I know this one, so I work out him to be 45. Again, with this top one, I can see a tangent. Does the tangent join to a radius to make 90? No. But what it does do, it comes in and goes back on itself and makes a 74-degree angle. So using this chord, I've gone from either end up here and said that that also must be 74. So I've called that ACB, with the little roof on the C. ACB is 74, my reason, alternate segment theorem. Okay, I know that's 74, given that that's 53, that's allowed me to work this one out because they add up to 180. So 180, take away 74, take away 53, actually gives me another 53. And when I read the question actually said, can you prove that ABC is an isosceles triangle? Well, I have, because I've just proved that these two angles here are the same, and in an isosceles triangle you have two equal sides and two equal angles. A bit of algebra on this one, great. However, what have I got? I've got a tangent. I've got a tangent going back on itself with an angle x. So I know that from there, if I got there, I've got another angle x here. Okay, alternate segment theorem. If you're given a reason, I haven't actually written that, but I should have. This is x because of the alternate segment theorem. Then I can see for the first time, I can see a diameter here. I've cut this into two semicircles by drawing that, and from a diameter, every angle coming from the diameter is 90, or the rule is an angle in a semicircle is 90. I'm asked to work out PQR, which is this blue one, but if these add up to 180, and I know that's 90, and I know that's x, then this one must be 180, take away 90, take away x. And then to simplify it a little bit more, 180 take away 90 is 90, and I can't do anything with a minus x, so that angle there is 90 minus x. Okay. Getting there? Start with the first one. lots going on. I don't think you've done anything this complicated with this much going on, but just look, they're all quite easy. There's a lot I can spot in here. First of all, the tangent. The tangent does join to the centre, so I have got a 90-degree angle in there, which I may use, I may not. But more interest to me at the minute is the 47-degree angle here, coming from the tangent, coming back on itself, and from there up to there. And I've coloured, hopefully you can see it, that I've coloured all that blue. So basically that is 47 degrees, and that's what I'm asked for first. ACB, this angle here. And the whole thing is 47 degrees because of the alternate segment theorem. Okay? But they told me this little bit was 23, so I've kind of worked out that this other bit, OCB, is 24, because then they would add up to 47. Which is what I know that is. However, I've also spotted a little isosceles triangle in there with a radius and a radius, making an isosceles triangle. So if that's 24 and 24, that's allowed me to work that out, because they'd add up to 180. Okay, and then once I know what that is, I've got that arrowhead, and the angle there is half of that, because the angle at the centre is double the angle at the circumference. My workings with is all this here. Okay, hopefully that makes sense to you. Nice easy one. Then I've got a semicircle, I've got a diameter there, so I know the angle from there again is 90. I know that's 90, I know that's 28, and I can work at x because they'd add up to 180. Last couple. Okay, tangent meets a radius at 90. So if I know that's 90, and I know again this side that's 90, and 30. I've got a four-sided shape there that adds up to 360. Not a cyclic quadrilateral, because it's not inside the circle, but still adds up to 360, and I know three of them, 90, 90, and 30. So actually, as it happens, this does end up being 150, which means that they do add up to 180, but that's not because it's a cyclic quadrilateral, but purely because these two are 90 and 90. Once I know that that's 150, that's half of that. You've got that arrowhead shape, angle at the circumference, half the angle at the centre, and the same here. Why have I left this one? Well, I've got my cyclic quadrilateral A, B, C, D, so they add up to 180. They're the opposite angles in a cyclic quadrilateral. Once I know him, AOC is double that, 142, and my reason I'd be given down here, so AOC is 142. I'm not going to write it, but my reason is the angle at the centre is double the angle at the circumference. However, what they want is ACO, which is this, and again, it's one of those sneaky ones. You got yourself a little isosceles triangle there, and I'd be writing all this down. But if that's 142, 180, take away 142 is 38. Okay, and so they add up to 38, but cut that in half. And that one's 19 degrees. Okay, we're going to jump past loci, which is the next topic, and transformations. We're going to do that in part 2 of the video, and instead we're going to take a look at page 18, congruency, to end this video. Now, let me again jump back to the notes. There are 4 ways to prove whether triangles are congruent, and by congruent I mean identical. First of all, if I've got 2 triangles where the 3 sides are equal, so on triangle 1, the 3 sides are equal to the 3 sides on triangle 2, they are congruent, and the reason I would give is SSS, side, side, side. If I can find SAS, a side, angle, side, but it's got to be in that setup, a side, and the angle's got to be in between the 2 sides, so which is why it's SAS, and I can find that setup on 2 triangles, they are congruent, okay? Or, if I can find 2 angles and I know the side between them, right, and the same on 2 triangles, I know that angle, and that side, and they're equal on 2 triangles, they would be identical triangles. Be careful with this one, mind, because if you know 2 angles, you know the third. So, once you know 2 angles, you know all 3, so you basically just could know any of the sides. As long as you know 2 angles, you know all 3. We'll see an example of that, and that'll make more sense in a second. And then the final one, if in a right angle triangle, if you've got 2 right angle triangles with equal hypotenuses, h for hypotenuse, and one other side equal, you can use the justification RHS. Be careful, 2 angles with 3 equal two triangles, sorry, with three equal angles, AAA, are not necessarily congruent, okay? One could be an enlargement of the other, so they were definitely similar, but not definitely congruent. Let's get to the questions. Page 18, I think we said. Okay. It just asked me to find pairs of congruent triangles and give the reasons. So the two I've gone for are D and E, because the three sides on D are equal to the three sides on E. So the reason I've given is SSS, three equal sides. Enough to say SSS. The other one I spotted was, if I looked at A, 3.9, 65, 4.4. So I've got side, angle, side, and importantly the angle is between them. Can I find that setup with the same numbers on another one? Yes, I can down here. 3.9, 65, 4.4. Same setup. Side, angle, side. So A and G are congruent, and the reason I'm giving there is SAS, side, angle, side. What else would I pick out here? Maybe just be careful that you didn't put B and H, because even though the three angles there are equal to the three angles there, all that means is that they're similar. They may be congruent, they may be identical, but it's not necessarily so that they are. Right. This. 37, 84, 37, 59. I thought, well, once I know two angles, I might as well work out the third. So I worked this one out to be 59, and I worked this one out to be 84. So actually what I've got here is two triangles with three identical angles. The three angles there are the same as the three angles there. But does AAA mean congruency? No, they might be, but not necessarily. So the answer here is B. Okay, and the reason I've given AAA means similar, but may be congruent, may not be congruent. And finally, okay, we've got it here. If you read the question, basically we've got to say whether the two triangles given are congruent, definitely not congruent, may be congruent, and if they are congruent, we've got to give the reason SSS, SAS, ASA, RHS. Top one, three equal angles means they might be congruent, but not definitely. So I've put not necessarily, definitely similar, but not necessarily congruent. These ones, there was two angles known, and a missing one, so I was able to work out the missing one. And actually, when I worked out the missing one, I found out that the three angles here were the same as here. The missing here was 60, the missing here was 56, so they are the same angles as these. However, on this one, the 7.8 lies between the 64 and the 56, so angle side angle is 64 degrees, 7.8, 56 degrees, whereas here, the 7.8 lies between the 60 and the 56. So it's a slightly different combination of angle side angle, so they are definitely not congruent. Okay, they've got the look that they might be because of ASA, but they're not. Whereas here, side angle side, side angle side, 7.2, 64, 7.8, 7.2, 64, 7.8. They're definitely congruent with SAS. And the last one here, okay. Again, I haven't got time to really talk you through everything here, so just to kind of cut it down on the amount I talk. What we're asked to prove here is we're told that ABC is an isosceles triangle, we're told that AP is equal to AQ, and we're asked to prove is ABQ, which I've kind of taken out there, this congruent to APC, yeah, which I've taken out there. Now, in the question it tells me that AQ and AP are the same. Alright, so I've put that single dash there. I also know that AB and AC are the same because I'm told it's an isosceles triangle, which I put there, AB equals AC. So I've got that side and that side being the same as that side and that side. So to prove they're congruent, I now either have to prove that the third side is equal, so I can use SSS, or the alternative is, because I've got side, can I prove that the angle between those is equal? Well, I can, because it's the same angle. It's this one here. Right? That is that and that. So side angle side, side angle side with the same two sides and the same angle in between. So I'm using SAS. A little bit more tricky to understand that one. And think we will leave that one there. That means in our final video on this, we're going to be looking at loci and construction. We're going to look at some transformations, and then we'll just have a look at some exterior and interior angles. See you shortly.